Okay, so the next talk is by MikhailPavlov, and he will talk about perturbative classical conformal blocks and holography. So thank you very much for your talk, which we are happy to listen to.
Okay, thank you very much. So, yeah, I'm MikhailPavlov, a graduate student at Lebedev Physical Institute, Moscow. And yeah, before I start, I would like to thank the organizer for the opportunity to make a talk. Yeah, so as you said, today I will talk about perturbative classical conformal block and its holographical description. So it's a pretty abstract work in ADS-CFT. So yeah, and of course, do not hesitate to interrupt me and ask questions. So yeah, this talk is based on these two papers with collaboration with my collaborators Konstantin Alkalaev. Yeah, and I would like to thank him at this point. And as a previous one, this talk includes two parts. The first one is devoted to conformal field theory calculations. So we discuss the Virasoro conformal blocks with heavy operators, the monodromy method of calculation of these blocks, approximation that we used, and we also introduce holographic variables, and I will list some explicit results of conformal blocks that we calculated. In the second one, we consider dual description of such blocks in terms of ADS3 geometry. So so I will tell you about role of background operators and perturbative operators. So we also discuss the emergence of holographic variables that I mentioned above. And finally, we will compare results obtained by these methods. So, okay. Let us start from conformal field theory. So we're interested in correlation function of the primary operators here. Yeah, the primary operator is the primary operator corresponds to higher weight representation of the Virasoro algebra, or in other words, it's an operator which transforms in most simple fashion under conformal transformation. Yeah, and the standard way to analyze such correlators is OP. So it's just an expansion of such product. In all primary operators in theory, G pi denotes the contribution of each primary operators and its descendants. Yeah, so having this, we can represent endpoint correlation function as follows, where f is called conformal block. Conformal block is defined only by the algebra. So yeah, here we consider two-dimensional conformal theory with the Virasoro algebra. So this block depends only on the weights of primary operators, of external primary operators, on the weights of exchange operators and center of charge. Yeah, and it's crucial that conformal block is theory independent. It defines only by the Virasoro algebra, and P here is a particular product of structure constant, which of this structure constant. So yeah, it should be mentioned that conformal block depends on the order of OPs. So so we consider so-called comp channel or C channel, where two first primary operators merge and give us the first exchange operator, which merge with the third one, and so on. So as we see is that, we see that any correlation function can be built by using and but a closed expression for such conformal block is unknown, so we need to use some approximations. The first one is typical, it's a classical limit where center charge tends to infinity, and also we consider so-called heavy operators. It means that weights scale. It means that the weight scale linearly at the central charge. It can be checked. It can be checked that up to sufficient order, that in this limit the conformal block takes this exponential form where f small is called classical conformal block, and epsilon eta epsilon tilde p are called classical dimensions. But also we need another one, approximation. We called it background perturbative approximation. So in other words, we suppose that there are n minus k. We suppose that n minus k operators are much heavier than k operators here. So we can see the picture. In this picture, the background operators are depicted by bold black lines. So it is example of 3 background operators, and here we have n minus 3 perturbative ones. Okay, so we formulate the approximation that we used, and a typical method of calculation here is monodromy method. So we start from an auxiliary block with an assertion of the generate operator V21, which corresponds to the generate vector of Virasoro algebra. And this auxiliary block satisfies the BPZ equation. In our case, it leads to Fuchsian equation 5 with function t, which is follows. So this Fuchsian equation is parameterized by accessory parameters C eta, Ce, which is just gradients of initial classical blocks. So on the other hand, the auxiliary block must have a specific monodromy when y goes around contours gamma k. These contours encircling points z1, z2 up to zk minus 1. And the main idea is to solve the equation 5 find the monodromy, the monodromy matrix of the solution of this equation, and compare with 6. But difficult to do. So here we implement the mentioned above perturbative background approximation. So we expand our block, our accessory parameters, and our function t up to the first order, trying to solve the equation 5 and find the monodromy matrix of solution. So yeah, doing that, we obtain the certain constraint on the accessory parameters. And here, we just express the first order monodromy matrix in terms of zero order solutions of the equations, of the equations 5. And this matrix takes this form. It's too complicated, hard to analyze. So we need to simplify our calculations somehow. And the useful way here is to introduce holographic variables. So let us consider holographic function, which is just a ratio of zero order solution of Fuchsian equation above, and yeah, and here we do and next we consider the following change, where when we are replaced, when we replace the position of perturbative operators by the values of holographic function W, and the idea is that yeah, it gives some simplification of monodromy matrix above, and we can see that we can express the monodromy equation only in the terms of these holographic variables. So yeah, we do not want to, we do not want an explicit form of the solution, because we can because we can just rewrite monodromy equations in terms of W. So it means that the first order correction to classical block and we formulate the uniformization property of such perturbative blocks, that in the term of holographic variables, the form of the endpoint block function is defined only by the number of perturbative operators and its weights. So yeah, in other words, we can separate the background part of the classical block from the perturbative ones, and the background part depends on the both variables that zeta, and perturbative one depends on the holographic variables only. And yeah, let me just list some results. So for some lower point examples, we can write the holographic function explicitly. For example, for well-known case of two background operators, the holographic function has this form. In the case of three background operators, we have this ratio which which depends on the hypergeometric function. And using this method, we can explicitly find the conformal blocks in this classical background perturbative approximation. So we can obtain 4-point blocks with the 3 background operators and 5-point block with 3 example to illustrate the uniformization property which I mentioned above. So the form of this block is the same that the form of 4-point block with 2 background operators up to the variable change. So it means, yeah, because these blocks have conformal block. It's an illustration of the uniformization property which I mentioned. So yeah, let us go to the holographic description. So let me just begin from the prescription. A typical prescription here is following. So so we need to do theory which correctly include the conformal theory on the boundary, and as usual it's ADF3, but the presence of the background operators deforms this geometry. So the prescription is following that the background operators can be described as some defects in ADF3, while perturbative ones can be considered as the prober particles propagating in this background. So let me just explain it on the simplest, well elaborated example. So for 2 background operators, we have the dual metric takes this form. So it's just ADF3 in global coordinate with the angle deficit, which parameterized by which is parameterized by alpha. So and the question is what we can say about 3 background operators. So in this case, we should start from the Benedes metric, which is solution of vacuum Einstein equations, and function h here is an arbitrary function. So in the context of ADF3 safety correspondence, its function can be interpreted as a CFT2 stress tensor. So its function tell us about the boundary. Yeah, tell us about the boundary degrees of freedom. So, but if we want to calculate something, we should reduce this complicated metric to simplest one. So one can see that so one can check that using the following change, we can reduce this metric to pure ADF3, and function W here is a solution of the following equation, and the good news that it is an exactly previously introduced holographic function. So it also means that this function contains all information about defects because our space-time is just ADS3 under this change. function W encodes on information about the background geometry. So, and in the case of two background operators, we can, we just have a conical singularity. In the case of three background operators, we have a complicated function W, but locally we can say that we have three defects parameterized by dimensional by classical dimensional background operators, and locally we can describe this geometry by conical defects. And as usual, in the case of three background operators, the perturbative part of the classical block is given by the action of probe particles with the masses epsilon eta propagating in this background. So for some lower point examples, we can calculate this action, which depends on the boundary conditions, or in other words, point of insertion of these particles on the boundary, and compare results with obtained by CFT. So, we can see that results coincide. And yeah, so it gives us an explicit check of the ADS3 CFT2 correspondence in this case, and also this method makes it possible to obtain an exact expression for some lower points conformal block. Yeah, and also these results can be implemented for studying entanglement entropy, out of time ordered correlator, the scrambling phenomena, and so on. And also it would be interesting to extend this method to second order of perturbative background approximation and see what's happening, because usual prescription with the probe particle doesn't work in this case, and it would be very interesting to do this. So yeah. Okay, so I think I finished. Thank you for your attention. If you have any questions, I'm ready to answer.
Yeah, thank you very much for your talk. Are there any questions? So, oops, what happened? Hello?
Hello, can you hear me?
Yes, can you share again your screen?
Okay, yeah, thanks. 1 second, please.
So yes, so you quoted like these holographic variables, like for 2 and also for 3 heavy background.
Yeah.
In the case of 3 heavy background operators, you implicitly assumed that 2 of the operators have the same scaling dimension, or?
Yeah. It's a very I think. Okay, so we can find the holographic function for 3 arbitrary dimension, but it has 2 complicated form. It also can be represented as a ratio of 2 hypohyometric function with really ugly coefficients.
Okay, and is there a constructive way to go beyond 3 heavy operators?
Okay, yeah, work is devoted to constructed way to go beyond, but it's It's complicated because we don't know an exact solutions of the zero order equation. In the case of for example, background operators, because we should solve this equation with the four regular singular points on the sphere, and we can solve this equation only in the we can present the solution only as a series, and it's hard to use this, but because it's hard to use it in calculations. So and then we just consider case of three background operators when we have some in some sense enclosed expression for holographic function.
Good. Are there further questions?
Can I ask one question? So these conformal blocks that you calculated, do you know to which operator do you actually exchange in your comp channel for these conformal blocks? I missed that. Do you know what are the exchanges?
Yeah. Okay, it's a very good question. So we also suppose that that exchange operator is heavy. Yeah. So.
So those are some heavy Virasoro primary operators.
Yeah, of course.
Okay.
And it's perturbative in the sense of the second approximation.
Okay, thank you.
Yeah, it's really important. I does not pay attention to this. Thank you.
So further questions? So then let's first stop here recording.
Yeah, thank you very much for your questions.